There's one thing.
For compressible potential. I will not speak about results for natural objects like sun or the earth, but only about an aspect in mean field theory for compressible flow. There is a very old result in mean field electrodynamics. Consider the induction. Could I just yeah, Matthias said yes. Matthias is here.
No, it's not on.
It's not on.
Yes, because of this. Sorry,
Is this now better?
Oh, yeah.
Yeah, okay. So, consider the mean field induction equation without a mean velocity and assume simply homogeneous isotropic mirror-symmetric turbulence, then the electromotive force E, defined in this way, is minus the constant times the curl of B. And this constant, yeah, you can put it in this equation, and then here is a mean magnetic diffusivity defined as original diffusivity plus this T, which is a consequence of turbulence. Okay, consider now small velocities, so that the so-called approximation applies, and consider the low conductivity limit, diffusivity limit, in which the ratio of lambda square over eta is the decay time for a magnetic structure with the dimension lambda, spatial dimension lambda, over tau c, which is the characteristic time for the velocity field, as the limit at which this quantity tends to zero. That means no serious time dependence on the velocity field. You can always put the velocity equal to a curl of a vector potential plus a gradient of a scalar potential, and you can say that the potential is, the vector potential is divergence free, and assumes that the averages over psi and phi are 0. Then you can derive this equation. It is not absolutely trivial, but it is a straightforward calculation, and this relation occurs, for example, in our book, Fritz Haus's and my book 1880. And by the way, there is an article we wrote in 71, and there's the same formula, but with a fatal error, not this minus here. And this minus is just so in this way, eta t can be negative, and so the eta m can be smaller than the molecular eta. 1 year ago, there was a winter school on dynamos here, and I gave a lecture about mean field electrodynamics, and I mentioned this, and Axel would not be Axel if he said immediately, yeah, we must investigate it and we must look how it looks numerically and so on. And so we started investigation about this. But we considered also the simpler case of passive scalar transport. This is an equation for passive scalar transport. C is a number density of dust particles or something like this. And again, no mean motion, homogeneous isotropic, neurosymmetric turbulence. Then the equation for the mean scalar looks like this, with a quantity f, which corresponds to the E in the actual dynamic case, for which you can write this. And so you have this diffusion equation for the mean scalar with Km, M means mean field. It is kappa, it's the diffusivity, the molecular diffusivity kappa plus this quantity. So, and you can repeat what you have done in the electric case, that concrete calculations are a bit different, and you find for this quantity Kt just this relation, with a minus here. That means the mean field diffusivity can well be smaller than the original diffusivity. Okay. Consider this under a bit wider assumptions. If the turbulence is no longer isotropic, you have this vector f in this form, the velocity-like coefficient gamma and tensorial kappa ij, and it is a simple exercise to calculate under the assumption of second-order correlation approximation these relations for the gamma I and the kappa ij, where the Q hat are the Fourier transforms of the correlation tensor, and very important is that these Fourier transform correlation tensors satisfy Bochner's theorem. By the way, Paul is not. It was Paul who drew our attention a long time, decades ago, to the importance of Bochner's theorem. Okay, I use it here again. So, specify this what I have shown you to the incompressible case, and the correlation length has to satisfy these relations. And then you find that this gamma is always zero, even in the non-isotropic case. And you find that the kappa ij is positive, semi-definite, in the sense as according to Bochner's theorem, the correlation tensor is positive, semi-definite. In the isotropic case, you have this relation, and you find that kappa t is positive, and so the mean field diffusivity is always bigger than the molecular diffusivity, as you expect. The usual idea is turbulence will enlarge these diffusion coefficients. But consider now the velocity field, the turbulent velocity field, which you can represent as a gradient. Then the correlation tensor looks like this, and according to Bochner's theorem, this R hat is a positive quantity. So then you can specify the relations I gave you before for kappa and for gamma and kappa ij in this way, and if R dot is markedly different from zero only for small omega, that means for time scales which are large, then you can drop the high omega terms and you get these relations, and you see that kappa ij is negative semi-definite. In the isotropic case, you have these relations with a kappa t which is negative. So that's the Km, mean field diffusivity, is smaller than the molecular diffusivity. Very remarkable. Okay. We go a step to mean field electrodynamics. Then in the mean field induction equation, you have this quantity which stands for U cross P, fluctuation U cross fluctuation P, and you have a term which contains the alpha effect. And usually here is Bijk and just the derivative of Bj by Ek. I split it in a part which goes with the curl of B, and the other part with the symmetric part of the gradient tensor. We should consider known helical turbulence, and we suppress the alpha effect, but we have the gamma effect. And I should remark that eta Ej in the passive scalar case, it is combined with the derivative of the mean scalar by xi, xj, and so it is, you can assume that it is symmetric. In the electrodynamic case, it is no longer so. The omega plus j effect, which has been discussed several times here, is described just by such an antisymmetric contribution to this eta j. Now it's the same game. You can calculate in second order correlation approximation these coefficients. It's just straightforward. You can consider incompressible turbulence, and you find that again this gamma, magnetic gamma I, is equal to 0 in the homogeneous case, even if the turbulence is not isotropic, and that eta ij is positive semi-definite, and you come again to it should be an eta here. The conclusion that eta t is bigger than 0, or not smaller than 0, and so eta m is bigger than the molecular diffusivity. And it is different if you consider again the irrotational turbulence, a turbulence in which the velocity field is given by a gradient. These are the general relations for this case, where the correlation tensor is replaced by the R proof. Again, consider the case where this R proof is only different from 0, or remarkably different from 0 for small omega, and then you can cancel these I omega terms, and you find that in the isotropic case, the gamma is equal to 0, the eta t is proportional to delta ij, with the eta t which is smaller than 0. By the way, the kappa t over kappa considered before in its dependence on it's just the same as the eta t over eta. No, it's the wrong way. So far, we have assumed ideal scale separation. So that's the quantity f, or the quantity script e, depends only on c at a given point and the first derivative on a given point, or e only on b and first derivative of b. As this is in general not true, or need not to be true, we will have relations like this, so that for example, f at a point x depends also on c and latency on other points, and here are kernels which describes the influence of the other points. Define, as we did Matthias yesterday, mean fields by averaging over x and y, and the mean fields depend only on z, and then this relation turns in this form. And of course, you come back to the original ideal scale separation relation if you make this and this to delta functions. It is useful to introduce a Fourier transformation with respect to z this way. Here the factor is a bit different from what I had before, but it is just useful for these purposes. And then this relation turns into this Fourier transform relation, and the gamma tilde and kappa tilde are just the Fourier transform of the kappa of the gammas. So, I think it is good to skip this, which I actually did. It is just a test field or test scalar calculation, as just in the sense as Matthias explained it to you yesterday. If you take for the mean scalar, for example, these test fields, you can calculate the gamma z and the kappa z depending on k in this way. I need not go into details. I will consider two examples. The first example is defined in this way. It is, how to say, a rough model of an isotropic turbulence. So here is the x direction and the y direction, or the x direction is not preferred over the y and z, and the y direction not over x and z, and so on. We define mean fields by averaging over x and y, but if we take, we consider quantities which are determined by u, phi, then we have at first a dependency on x minus psi. It should be a random variable, and eta tilde also a random variable, and theta tilde. The averaging over x and y is an equivalent with averaging over these random variables, but there might be a dependence on z, and that's why I say, in addition, we average over this theta tilde. In this way, we come to a, say, homogeneous turbulence. Okay, in this case, we should have this relation, which I explained before, and analogous relations for the mean electromotive force. And we can make, again, simple Soccer calculations, and we find that kappa t, I remind you that the tilde means the kappa dependence is a constant, here minus a constant times the Peckley number, or eta t is a minus a constant times the magnetic Reynolds number, and the function of k here, kf is just a bit different, a bit modified k0. This function may well be negative. It is positive for k over kf. E stands for k over kf. Smaller than unity, and it is negative later. Okay. This way. So far, we had second order correlation approximation. And the results calculated in second order correlation approximation lie on this line. And here now are calculations by the test field as the scalar method, and you see that they differ from the Zucker calculation as soon as the Peckley number or the magnetic Reynolds number exceeds, say, 0.5, something like this. By the way, these are calculations made for very small ratio K over Kf, so that we can assume that these quantities with the tilde agree with the quantities without the tilde, and this I first show you here. Here K tilde over something independence of K over Kf for a few values of the Peckley number, and you see if this K over Kf becomes very small, it tends always to constant value, and the same for eta t. Let's look again on this diagram. The first what I want to mention is the dependencies of kappa t and eta t on Peckley or the magnetic Reynolds number are the same in the range of validity of the second order correlation approximation, but there are deviations from each other for kappa and eta later for higher values of Peckley or magnetic Reynolds number. So if you make only second order correlation approximations, you have the feeling it's always the same, but it is by not. The compressibility effects are stronger in the magnetic case, in the eta case. Now I have to explain this shadowed area. If the curves come to this region, then kappa plus kappa t is negative, or eta plus eta t is negative. That means you have no longer a decay of the quantities, but a growth of quantities. But fortunately, these curves come not to this region. They remain always in the region where the sums of the molecular quantities and kappa t or eta t are positive, so that we can conclude there is always a decay of the quantities. What else I have explained? I made the assumption that this parameter Q I defined before, which is 0 if the velocity field doesn't depend on time, that this parameter Q should be small for the results I derive. Here we have considered velocity fields which are no longer constant in time when we consider a renovating flow. That means the flow is constant, time independent over a certain time. Then it switches to another flow which is not correlated with the flow before, which exists again over interval tau and so on. And calculations have made with this renovating flows, and you see negative coefficients kappa t and eta t are in a region of q up to say 0.2 or something like this, small q. So this effect of compressibility that the kappa t and the eta t becomes negative is restricted to small q. And also, if you look at the picture I shown before, here, and also, of course, to small Peckley or magnetic Reynolds numbers. Okay. No, I made it wrong. Second example, we consider a model of a strongly isotropic turbulence. We construct the velocity field as a superposition of sound waves. So with a given k, a given wave number and a given omega, and a phase shift phi. Again, consider and such a sound wave, if omega 0 is not put equal to 0, has automatically a Q which is different from 0. It's not 0. Okay, we define again mean fields by averaging over x and y, and now over this phase shift z, and we assume, it's not an assumption, is so, that the f has this structure, and then we can calculate in second order correlation approximation this gamma depending on k, and this kappa depending on k. This is a bit complicated. Not the calculation is not complicated, but the dependence of these quantities on k, and and I should mention that I also assume that the mean field varies like exponential lambda t, so also on lambda, and on the epsilon I explained before. Q is complicated. Consider simply the interesting point is that in the ideal case, if you put the Q equal to 0 and epsilon and W equal to 0, this kappa ZZ over K has a singularity, where K is equal to Kf. That means it takes negative, or you can always have arbitrarily large negative values. And so you would expect that if you are in this region where it is strongly negative, the mean quantity does not longer decay. And that's, of course, very exciting, and we made some investigations of this. First, it is a Zucker result. And if you deviate from Zucker, then it is no longer so. Here is the region where the kappa plus kappa tilde, that's it, is negative, and you see the curve doesn't go to this region, but it comes very close to the border of this region. Okay, you can now take the calculated values of kappa zz and can calculate decay rates. These are the decay rates of structures which are proportional to the cos or sine kz. And if you take the calculated values for lambda equal to 0, then these the decay rates are by a factor of about 20, one example, of about 20 larger than the decay rates observed in direct numerical simulation. You can follow up the decay in a direct numerical simulation. And this is, of course, a very exciting discrepancy, and it can be explained by the memory effect, which was investigated by Alex Hubbard and Axel Brandenburg 2 years ago. Here I can simply say you have to calculate the kappa zz independence of lambda, of the growth rate lambda, and if you do this, then again this discrepancy vanishes. Okay. Yeah. I hope I have shown you that there are considerable effects of compressibility, even but in a range of a small Becquerel number and small magnetic Reynolds numbers, and then this coefficient Q, which describes the time dependence of the field, is not too large. Okay, I think that's all. Thank you very much.
Thank you very much. Questions, please? Okay, fine. Yes, sir.
Concerning the anisotropic case,
Yeah?
you remember that we calculated the turbulent diffusivity for the geo-Roberts flow in the Soka approximation. I showed this curve yesterday, which becomes negative after some magnetic Reynolds number.
Yeah.
And did you try to compare the formula that you found to these results?
Yeah, I think these are two cases which are not easy to compare. I consider here simply sound waves traveling in the same direction. And
I'm talking about a stationary flow with which is anisotropic, like the geo-Roberts flow.
mm-hmm.
That's a non-Soka result already, which is of course correct and confirmed.
No.
And it's incompressible.
It is incompressible.
He is talking about compressible things, and already in Soka it becomes negative.
But it was also in Soka, in our case.
Yeah.
What's wrong with Soka?
But I think it has nothing to do with this, because here is compressibility issue.
And you said that even when going beyond Soka, this result in the second model remains positive, but comes very close to the margin of the negative area. So is there a theoretical reason why it cannot cross this?
I could say, why then a dynamo-like situation would occur. And there are good reasons to exclude a dynamo. Here, say, in the passive scalar case, it would mean that there is an infinite concentration of particles or something like this is produced. And unfortunately, I have no theorem of the type of the anti-dynamo theorems which excludes this, but I think it is fairly clear by physical reasons that you cannot expect infinite growth.
Yeah, but in reality there wouldn't be an infinite growth. There would always be a self-limitation, so branching also.
Yeah.
So that physical argument, I don't see that it's really ruling it out.
I mean, the passive scalar concentration is just described by the Lagrangian evolution equation. And so therefore, it should go beyond the limits that are initially defined out by the passive scalar profile.
Yeah. You may
That is the theoretical reason. But the decay can be incredibly slow. And then Karl Heinz said that the test calculation gave a 20 times larger value. I should put it the other way around. I should say that the actual calculation made it 20 times slower still, which is unconfirmed with the test field method.
20 times slower compared to the case where already this kappa ZZ was considered.
Yes.
But a wrong value of it was considered.
In comparison
And
to the
it is even a larger factor if you compare it with the case without turbulence.
That's another big factor again. Yes, it's a real and extremely considerable reduction.
Okay, thank you. Okay, so in your calculations, Q has a sense of inverse truthful number.
Of Reynolds number divided by 200.
Reynolds
Exactly Reynolds divided by 200.
And you obtain them if you inside in the framework of a quasi-linear approach, then diffusivity, contributions of compressibility to diffusivity of passive scalar and to magnetic diffusion is the same. And then, and when you increase the clear number or when it's no Reynolds number, you obtain deviations. Yeah, that's good. Okay, thank you very much, Karl-Heinz. The next talk will begin by making theory. So this is compressibility effects on turbulent MHD and passive scale transport. And
Actually, can you my jacket?
Compressibility effect on turbulent MHD and passive scalar transport. No, this talk was, how to say, in some sense, congruent with Karl-Heinz talk, because when we listen about this phenomena of depressing of turbulent diffusion in presence of compressibility, we immediately produce calculations. Not only, first of all, we try to reproduce calculation in SOCA approximation, and after that, not only in SOCA. And no, what I would like to pay attention on this picture of two real turbulence, and what where is pointer? This one. And this picture is real picture from laboratory, and you can see a lot of small edges. But of course, in parallel should maybe compressible part. If a 2D picture, sometimes you can see a region of convergence and divergence. It should be something in the spirit, and of course it will be 3D. It is just 2D, and we observe 2D convergence, and because Mach number is very low, we got, of course, compressibility very low. But nevertheless, of course, it is maybe interesting too. Okay, no, it is work was done with Zimmerman-Lachevsky, we are working together almost 2 years. And with Axel Brandenburg, we try to study numerically what we find. And let me start from outline. I would like to discuss briefly properties of compressible and compressible turbulent flow, relation function in this case, turbulent diffusivity and pumping of magnetic fields, turbulent diffusivity of passive scalar. And unfortunately, numerical evidence, I've got some technical problem to open our pictures. I'll explain by hand what actually happened, and let me continue. Okay, now in order to study classical problem, pumping and so on, and diffusion, for magnetic field, of course, we can start from induction equation, and after averaging, formal averaging, it's possible to understand that main, effect which we should calculate, it is electromotive force, V cross B. V is fluctuation of the dynamic field, and B is fluctuation of magnetic field. And after that, say in low conductivity limit, we can find fluctuation of magnetic field, and if we now calculate V cross B, we will find the electromotive force. I would like to say that from this expression, obvious that there is two contributions, one proportional to magnetic field, and second one to derivative of magnetic field. Q is this wave vector of Fourier decomposition of mean field magnetic field, and of course we will arrive to well-known result of Karl Heinz and Radler, Fritz Krause, and Martin Steinberg about two contributions, one proportional to mean magnetic field, second one to derivative of mean magnetic field, and it is the same general, how to say, expression that Karl Heinz demonstrates now. But I would like to go a little bit, how to say, in more partial results. I would like to discuss a very simple model when turbulent isotropic, in the beginning homogeneous. In K-space, it is correlator of velocity field proportional to projector operator. And of course, immediately we will calculate second contribution equals 0. But first note, it is well-known result for this. It is just turbulent diffusivity, and I simply discuss in this consideration very simple model when just actually one scale of turbulence and one frequency dependence very simple, just proportional to delta function. But in the frame of this simple approximation, nevertheless, pumping again equals 0. In order to find pumping, we should phase 2 in homogeneous turbulence, take into account in homogeneous. That is known how to do it. We discuss now just in homogeneous turbulence without any effect of compressibility, even without influence of homogeneous density. But nevertheless, in this case, pumping exists, and this term it is nothing else than effective velocity, which of course proportional to gradient of turbulent diffusion. Interesting, if we take into account gradient of density, and so we will discuss our flow not in incompressible case, but an elastic approximation. Nevertheless, we didn't find in new effects, we will get the same. It means that classification of density doesn't influence of pumping. It is true in linear approximation, in kinematic approximation. If you take into account nonlinear effects, we of course we will find the influence of gradient density of this pumping. Now let us discuss how to calculate correlation function for compressible velocity. Let's start from Hilbert's theorem, which said that all vector and of course velocity field can be described as a sum of two contributions. Divergence free, which proportional to curl of some vector potential, and potential part, which proportional to gradient of scalar potential. And we discussed isotropic case only, but nevertheless it gives us very enough interesting and, if you like, rich result. For example, if we now calculate correlator Vi, Vj, and we will do it this way, we need to put minus here in this position, and we just calculate product of these two expression, which it is just Fourier transformation of Vilgo's theorem, we will find, of course, 4 terms after everything. And you can see this first term, it is something proportional to incompressible part, second to compressible part, and some 2 terms which it is, how to say, product of compressible and incompressible part. We will, because we discuss isotropic situation, it means that this correlator AMAN should be proportional or delta MN or another contribution MKN. We haven't enough vectors in our situation. And second term proportional to some scalar. And these 2 terms may be proportional to some vector, but vector only one again, it's just K. It is very easy to see that these 2 terms immediately disappear because we've got KP say and KM together. It means that this term equals 0. The same, of course, next, because it's just same, practically the same term. So we've got separation between incompressible part, incompressible. It's interesting. It is very, how to say, general result. It doesn't depend on in general, in isotropic case, it's a general result. Now we can calculate, continue our calculation, we will see that second term doesn't contribute, because again for the same, for symmetry reason, because we've got KMC and KP, and what we've got just delta MN. And when we put this delta MN, we produce a projector, we will get projector operator, nothing else. And so we will find that 2 contributions, one proportional to projector operator, it is Ohm's result, and U is proportional to Ki, Kj, and it is so now we are ready to work and to contribute and to calculate the motive force. By the way, sigma t is parameter of compressibility, and in the case when and for simplicity we will choose this function which describes spectra of incompressible and compressible part as a power law spectra. If this power is the same in this situation, this sigma t is just its ratio between divergence V square average and curl V square average. So it is, in some sense, it's a ratio of irrotational and rotational part of this turbulence. If it's not true, it means, for example, P larger than Z2. In this situation, we should use just NZ contained scale for calculation, and our definition will change a little bit, but it's not so serious, I think. Okay. So now, next step, take into account density stratification. We can do it, and now we've got general representation, which we've got both isotropic part, rotational, irrotational, and 2 contributions. The contribution of inhomogeneity of turbulent velocity, and second one, contribution from inhomogeneity of density. And some function which is sum, very symmetric sum of irrotational part and rotational part. So now, next step, calculation of electromotive force. It is our result. By the way, it is in total agreement with the result of Karl Marx. We, for small Reynolds number in Soka approximation in low conductivity limit, we find that turbulent diffusivity has 2 contributions. One is rotational, second one compressible. And what's interesting, that if sigma t, if law of compressibility enough high, this turbulent diffusivity can be negative. But of course, again, total diffusivity positive. because this effect in general proportional to magnetic density squared, and this is of course like more than unit. Interesting feature of this stuff that effective velocity for effective why the same formula, it's in the classical formula of Karl-Heinz minus gradient half of gradient of turbulent viscosity. Okay, what else? No, if of course if Q and P equal, we've got a little bit more elegant formula, but it's not very important. Okay, now if we take into account inhomogeneities, sorry. Now let us discuss this result for large Reynolds number. In this case, we use our approximation and find another result. First of all, its main difference that for large magnetic Reynolds number, the turbulent contribution to diffusion will be positive in any situations, our result. Second, if we, the same good result which simple says that effective velocity is just minus half gradient of turbulent diffusivity is not true, unfortunately. But what's nice, if P equals Q, in this case we've got 1 divided by sigma T divided by 2, and these two factors cancel, and we almost arrive to all expression without any sign of compressibility. Okay. Okay, now what about passive scalar? No, passive scalar, we know several examples. It's temperature, number density. We choose, I choose here just temperature, because if you push, you put gamma equal 2, you immediately come back to number density, passive scalar of number density, and it is our result. What's the difference? No, first of all, the Clay number is a magnetic number, the same. Turbulent diffusion in low conductivity limit, the same as for magnetic field. Velocity, effective velocity, no, it is natural because if divergence V equals 0, no influence of gradient of V square, as Karl-Heinz demonstrates, something happens just in presence of gradient of density. Nevertheless, if you take gradient of compressible part of turbulent diffusion, it will be precisely the same formula minus half gradient of, in this case, of compressible part of diffusivity. Okay, interesting what we've got. We've got additional term which is proportional to gradient rho divided by rho. In some sense, we restored our old result with Igor Gachersky and Tov Alperin about so-called turbulent thermal diffusion. So it's not a surprise for us. It is, but next step maybe will be more interesting. Now, if we discuss a large Pictet number and face to this story again, what we see that turbulent diffusion positive again, no doubt. But what we, in reality, we will see in this situation. No, we thought with Igor, honestly speaking, that it is not important, this problem, because we have gravity in this problem, no reason for serious gradient density, serious densification, but not so simple situation. In order to increase influence, first of all, we discussed with Axel and decided to check it numerically. And what's interesting, we find just opposite result, because according to this calculation, particles should be accumulating the maximum of dynamic energy. But Axel finds something opposite. The reason in this second term is to take, in order to get large sigma t, we try to increase Mach number. When you increase Mach number, you increase velocity field. If velocity field will be more or less of the same order of sound speed, you should take into account influence of turbulent pressure. If it's true, you will produce gradient of density certification. And now if we take into account this fact, this is for total pressure, means pressure, which sum of dynamic contribution and turbulent contribution, and you can calculate that in this case, if say velocity field will be function of depth, as the density will be a function of depth, m squared is a function of depth. So if you carefully calculate gradient rho divided by rho, you will find very nice formula. And for simplicity, I put in this formula P equal Q. And what we find, if Mach number enough large, say 5 or 3, this is almost 4. This 5. If you compare it to this guy, it's maximum 2. So it's obvious for large Mach number, we should get, instead of accumulation particles in the maximum of turbulence, in the minimum. Should. So similar to diamagnetic. For me, was big surprise that Axel, when he and it is true. What Axel find for small large m, it is really accumulate in the vicinity of minimum of turbulent velocity. But what big surprise for me when Axel suppressed Mach number seriously, he finds nevertheless this effect. It is really strange. So it's our result. Unfortunately, I cannot demonstrate numerical result because I didn't successful to open your picture, actually, but I can, how to say it, maybe to give a small sketch on. But what we find that if we've got it is profile of P square, we find that in this situation when Mach number was about 3, we find something in this field. This effective velocity. Okay? And when Mach number was close to 0.3, we find that opposite situation. But one more smaller. And so it means okay, that's good. you can see that what we absorb. So for large we absorb this red, and for small, no, it is part of what we need. No, never mind. It is for small Mach number, right? No, it's small. It's small. Because we will see for small Mach number, what we see that turbulence increase when Z increase, we absorb negative velocity contribution, and when turbulence decrease, we got positive, negative. And so it is precisely according to this formula that very effective proportional to gradient of turbulent diffusion, not minus gradient. Okay, thanks for your attention.
Okay, thank you very much. I only would like to say that main difference between the work which Karl-Heinz made and this work is that here we have turbulent velocity field, and Karl-Heinz considered the deterministic velocity field.
Not only that.
Yeah.
Turbulent too, but not only. In turbulent case, it's not only in turbulent. Both cases would be in turbulent.
Okay, question, please. Yes.
I have a very general question. You presented this compressible approach, but how do you treat the presence of the shocks?
Now, it's a good question. What does it mean, isotropic ensemble of shock waves? If you can imagine, it should be the same practice.
No, I have one shock wave. It's enough
one shock wave. In order to introduce shock waves, you've got two possibilities. Or believe in some, for your turbulence, say after shock wave, is isotropic, but feel some gradient in direction of propagation of shock wave. Is it true? Our representation is okay. you should, if you gradient enough strong, you should take into account quadratic contribution, which I skip. If not, I think we've got only one way to build general representation for isotropic turbulence.
So, to be more specific, do you think that the turbulence will propagate along the characteristic in presence of a shock?
I'm not sure that it is turbulence.
But this is turbulence.
Yeah, I am not sure that turbulence exists in this situation. Yeah. It's another story, because precisely in shock waves, normally no turbulence. After, before, please. But not in turbulence, in shock.
Okay.
I mean, shocks, as far as the numerical method is concerned, we just run larger and larger Mach numbers, and of course, the larger the Mach numbers, the more shocks we get. And then you get into the other regime, different from this one, which is on the next page, where the two begin to agree more and more.
Well, how do you numerically handle the shock? What's your
By just resolving them sufficiently. So if you have a Mach number which is getting 4, and you want to have a large Reynolds number, you have to have many, many mesh points.
That's not enough. Sometimes we do
No,
get wiggle.
it must be enough. If you must then otherwise restrain yourself to smaller Reynolds numbers.
That's enough.
If you can't have the mesh points. You can, of course, do a shock diffusivity, but you better check first of all that that gives the same result. That you have to check first.
Okay. Thank you very much. Next talk we will be doing by Steve Device, direct statistical simulation of
Needs to change the resolution.
Small announcements. First of all, we're going to have a conference picture. Hopefully, where's CK? CK? No, CK is not here. He's probably checking out the place. The idea is to do it on the staircase outside with the tripod of our camera here right now. The other thing is, if people already want to get a
When is the photo?
The photo is during the next break.
Okay.
So that means, and let's do it first during the break. That means at 13:25 or something. I have a few of these little cards which gives the location of the restaurant, which you find also on the internet, on our homepage, on the conference homepage. Some people had this card, others didn't have it. Technically speaking, it's also possible to get
trigger the auto adjustment of the
technically possible to get actually everything on foot for those people who want to really run the whole distance. But it's not really necessary. You can also take the red line, or any of the metro lines. You go through, you don't need that. You go through Central Station, one more stop, and get off at Gamla Stan.
after all that hardcore mathematics, a few gentle pictures to take us to I'd like to talk about astrophysical and geophysical fluid dynamics using direct statistical simulation. I wish we hadn't called it direct statistical simulation. It's a very difficult thing to say when you're giving a talk. What I've decided over the years of coming to dynamo conferences, Karl Heinz and various other people, is that dynamos are very hard. So I'm not going to apply any of my ideas to dynamos today, but hopefully in the future maybe we'll be able to apply some of the ideas to dynamos. So I'm going to talk a little bit about astrophysical modelling, and this should be old hat to you guys, so I'll go very quickly through this, and then I'll talk about the differences between dynamics and statistics, and I'm going to talk about a method of solving equations using what we call direct statistical simulation. We're going to use a hierarchy of cumulant expansions. I'll explain what I mean by that. So let's just get started. We've all seen astrophysical objects. There's a large range of spatial and temporal scales. This is Jupiter. It's quite a big planet, but not as big as some of the things we study here. And of course the difficulty is in resolving all these scales. And the large-scale behaviour is often driven by things that are acting at more moderate scales. I just want to stress that the turbulence is often inhomogeneous and anisotropic. Like here we have this very inhomogeneous system. We get these nice jets, which I'll show you on the next slide. So it's very anisotropic as well. And this is very different from homogeneous and isotropic turbulence. Other examples, which we'll see, the interiors of stars or in accretion disks. So this is an example of inhomogeneous mixing. These are the jets that are formed at the surface of Jupiter, or one theory is that they're formed at the surface of Jupiter. And the models for this is that the small-scale turbulence drive the large-scale jets. So if you were trying to parameterize this using an eddy viscosity, like we heard before, you would actually need a negative eddy viscosity, because the large scales are emerging from the small scales. Okay, so this is an example of the sort of thing that Karl Heinz was talking about. This is actually a negative eddy viscosity in action, if you want to think of it that way. The interior of stars, again, they're very inhomogeneous and anisotropic. And here the differential rotation profile that we see emerges from the turbulent interactions. This is often parameterized maybe by a lambda effect or whatever, and I'll come back to that later on. So again, small scales here are driving a large scale flow. Finally, in experiments, these are still often inhomogeneous and anisotropic, and there are lots of small scales and large scales interacting, and we want to get some idea as to how these small scales and large scales interact. So what do we tend to do? Well, there are various different astrophysical modelling strategies, and we heard a lot about some of these strategies over the course of the conference. But I think probably at the moment, by far the most popular is direct numerical simulation. So what do? We just discretize the equations, capture a range of spatial scales, because we only have a certain number of modes on our computer, and then we either say we're going to invoke some kind of eddy diffusivity for the scales that we can't capture. We either accept that we're in the wrong parameter regime, this is in some sense the most honest thing to do, I guess, or just adopt a closure of small scales. And this is very, very good at describing the dynamics of the system, but it's very expensive to calculate statistics. We're quite often very interested in statistics, but what people do when they run a DNS is they go to the highest parameter value that they can get, the most astrophysically relevant, and then it turns out that they don't have as much computing time as they'd like, and they only calculate for a very short length of time, and they can't get very meaningful statistics. So here's an example which you all know of state-of-the-art DNS trying to understand that problem of generation of differential rotation in the solar interior. And these are the simulations by the Boulder group. These are massively parallel, amazing computations of anelastic convection, and they run them for as long as they can. They get some mean properties. They average for a length of time. They get some mean properties emerging, and they try and work out how the mean flows that emerge relate to the smaller scale stresses and turbulence that's driving them. And if they do something different, like they change the boundary conditions, here they've changed the entropy boundary condition from this case to this case, they have to run everything again. So it's very expensive and quite difficult to do. Okay, then the other extreme, one might say, of astrophysical modelling is to construct mean field type equations, and I don't really need to introduce these for this audience. These are great because you solve only for the large scales, and then you parameterise or try and calculate from models the effects of the smaller scales via transport coefficients. So it could be the lambda effect, the alpha effect. And often this closure is achieved by fixing the behaviour of the large scales. Okay? This is what Professor Parker called the quasi-linear approximation. And of course, sometimes we've heard a lot about non-locality. We heard from Matthias yesterday that we should have non-locality. Usually, or quite often, local approximations are made, but the transport coefficients are really non-local, as pointed out by Karl-Heinz in his talk today, and on many occasions. This EMF is related to the mean field, and you really need to know the mean field at all points in space and all points in time, previous to where you're trying to calculate it, because this, of course, is described by a differential equation. And so you want to know something about how the cross-correlation, this Green's function, how this behaves, the correlation between the point x that you're interested in and all of the points in space, which is a difficult thing to achieve, I think it's fair to say. And people try and do this. Usually they do kind of one-point closures. So, for example, if you were trying to calculate the Reynolds stress, or perhaps the EMF as a point, then what you try and do is you relate the Reynolds stress, say, to mean quantities at that point, or if you want to be a bit more fancy, maybe to their derivatives. So you might say the Reynolds stress, the fluctuating mean of this thing is some function of your large-scale variables, and then you try and get the transport coefficient either by doing lots and lots of local analyses using, again, massively parallel computations, or you just put in plausible profiles.
What is alpha in this?
In this paper?
Yes, alpha.
Alpha.
Alpha, F-I-G.
Okay, so this is by a paper by Pascal Garot and Gordon Ogilvy, where they derive an evolution equation for the Reynolds stress. This is a parameter that they're putting in. It's not the alpha. It's not alpha. This is for the Reynolds stress. Okay. Quite often, we're not interested in the dynamics. We're interested in the statistics. If we're running an experiment, we might want to know the mean torque that you need to apply to overcome the turbulence, or in Jupiter, you might want to know what the mean effects of all the vortices are in driving the large-scale flows. So I want to make this distinction between dynamics and statistics. So dynamics gives the detailed behaviour and interactions, whereas statistics gives the average behaviour and the correlations, which is something we're interested in. And Mark Twain, my collaborator, is a climate physicist, so he pointed me in the direction of this quote. So climate is what you expect, but weather is what you get. Okay, so if you're interested in the dynamics, if you're really interested in when some vortex is going to land on your head and, dump all its rain on you, then you're interested in the weather. If you want to know the mean temperature in 100 years, then you're interested in climate in the statistics. And I'm going to try and introduce a method for calculating the statistics of flows directly. So you solve equations for the statistics directly. This is not a new idea. Indeed, Lorenz, the very famous meteorologist, he was not a big fan of just doing DNS and trying to work out what happened. He said, more than any other theoretical procedure, numerical integration is also subject to the criticism that it yields little insight into the problem. The computed numbers are not only process-like data, but they look like data. And the study of them may be no more enlightening than a study of the real meteorological observations. Now, I think that's a bit harsh for astrophysics, because we don't really have any meteorological observations. But nonetheless, I think he has a point. He does say an alternative procedure which does not suffer this disadvantage consists of deriving a new system of equations whose unknowns are the statistics themselves. So this is what I'm going to try and do. He goes on to say this procedure can be very effective for problems where the original equations are linear, but in the case of non-linear equations, the new system will inevitably contain more unknowns than equations and can therefore not be solved unless additional postulates are introduced. So what I'm going to do is introduce some additional postulates and try and solve some equations. If one is interested in statistics, then there might be some advantages, and indeed there are. if one is interested in statistics like means or standard deviations, then these tend to be smoother in space and stiffer in time. The equations are stiffer in time than if you're calculating the dynamics. So one might hope that you can describe them with less resolution in your numerical scheme and access them more rapidly. Okay. One also might hope that whereas the individual dynamics is sensitive to the parameters you're looking at, so for example if you increase the Reynolds number in a flow, whether a vortex is going to land on your head is probably going to be very sensitive to the Reynolds number. The statistics might be less sensitive. That is the hope. And I guess that is the hope for when you do turbulent transport coefficients as well. So let me introduce cumulate expansions, and if you want to know the details, then I suggest you go and ask Professor Frisch, who's sat outside, because it's all in his book, so that's good, you can all go and ask him. And let's imagine one has a differential equation. This is a very simple, ordinary differential equation that looks like it has a linear term and a non-linear term. Then, what one can do is take the mean value of that equation. So one takes the expected value of the left-hand side and the expected value of the right-hand side. Think of this as an ensemble average, if you like. And then I'm going to define the first cumulant as the expected value of x. So this is a bit like the first moment, okay? And I can derive an evolution equation for the mean, which is something we're all used to doing, by saying C1 dot is just AC1, that's true, but then I need the expected value of x squared, which I don't have, okay? So I need to define a second cumulant, which is like the standard deviation, okay, to be the expected value of x minus the expected value of x all squared, okay? If you do a bit of rearranging of this, you can see I can get the expected value of x squared in terms of the first cumulant and the second cumulant. So I can derive an equation that looks like this, okay, but unfortunately my equation for C1 has C2 in it. When I carry on, I'm going to derive an equation for C2, which is going to have C3 in it. So I'm going to get an infinite hierarchy of equations. And this is what Lorenz said, you can't solve these unless you introduce additional postulates. So that was an ordinary differential equation. Well, let's say we have a PDE, which is not all that much more difficult than an ODE. Once you discretize it using a standard technique, okay? So we'll discretize it using your favourite discretization, spectral basis functions, a finite difference scheme, or finite elements. And so then you get a system of ordinary differential equations. Okay? So we could solve these as a system of ordinary differential equations, just do the direct numerical simulation. Or we can define the cumulants using some form of averaging. You guys are all used to the various different forms of averaging. We could do a time average, an ensemble average, or perhaps we might average over phi, over longitude. So if you do this, and you just do exactly the analogous procedure that I did on my ordinary differential equation, you derive a system of equations. Okay, let me define the cumulants first. So let's do the standard decomposition. I'll take my variable, and I'll take a mean and a fluctuating bit, where the mean and the fluctuating bit is 0. And I'm going to define my cumulant. My first cumulant is going to be the average. So this, for those of you who know about moments, I'm going to relate these cumulants to moments. So the first cumulant is just the first moment. The second cumulant is what's sometimes called the covariance matrix. It's the thing that encodes all the information from different locations in space. So this is the correlation of Qi with Qj. We take the average of this. And this is how one can write it in terms of the moments. Okay, so that's the first cumulant, the second cumulant, and one can go on defining the third cumulant and higher order all the way down. And then again, we use a fancy technique to derive equations for the cumulants. You don't have to use the hot functional technique, but it's a very elegant way of deriving the equations that you get for the cumulant. So I'm not really explaining how I get these, but anybody who's interested can ask me later. Okay. And again, you see I've neglected the fourth cumulant here at the minute, but if I were to be rigorous, I should keep in an infinite hierarchy of equations. And what usually one can do is truncate this at either second or third order And this is all well known. This is all old stuff, but it leads to very expensive calculations, because if one thinks about the equation for this second cumulant, let's say I started off with a two-dimensional equation, a two-dimensional PDE. My equation for my second cumulant is four-dimensional. So I've taken my two-dimensional PDE and immediately turned it into a four-dimensional equation, which those of you who do numerical simulations know is a completely dumb thing to do. You don't want to start solving 4D equations. But sometimes you can use the symmetries of the problem to increase the computational efficiency.
Excuse me, what is it AI and BIJ? I understand C is some variables you can model.
This is the second cumulant. Okay, so if you go back, these arise from your original equation. So this was your yeah. So those are the coefficients in your ordinary differential. Okay. If one truncates at second order, then there's a very understandable procedure that you're doing. What you're doing, and this is a bit like soccer in a sense, you're keeping the mean eddy going to eddy. So you're keeping the mean eddy going to eddy interactions. You're keeping the eddy going to mean interactions. Okay, but you're discarding the eddy going to eddy interactions. Okay, so you're losing any chance of having a cascade or an inverse cascade in your problem. Okay, if you go to higher order, then you can keep a cascade in your problem. The nice thing about truncating at second order is that there are various properties of the equations that are nice. The equations are realizable in the sense that because we're calculating probabilities, one would quite like your probabilities to be positive, and you don't really want negative probabilities. So they're realizable, they're well behaved in the sense that the energy density is positive. What is very nice about these equations is that if you're dissipationless and your original equations conserve certain quantities, then your cumulant equations conserve certain quantities. So for example, you would conserve total energy, magnetic helicity, mean square potential, all of these things, if your original equations conserve them, then these do. So if one were to ever get applying these to dynamos, and you think conservation of magnetic helicity is very important, then your cumulant equation would conserve. There is no need to truncate at this order, and of course you can include higher orders. And if you truncate at third order, then these tend to have an ad hoc parameter to ensure realizability. And those of you who know about EDQNM, eddy-damp quasi-normal approximation, will know what you have to do is damp some of the eddies to ensure realizability. So this now includes the eddy going to eddy interactions. Okay, that's an introduction to cumulants. I'm going to do a very simple model problem, but a simple problem that has non-trivial dynamics. I'm going to do two-dimensional MHD on a spherical surface. Okay, so this is not dynamos. It can't be a dynamo. We're doing 2D, and this perhaps is relevant to the tachocline or the outer layers of some extrasolar planets that might be magnetized. And this can be written in terms of the total vorticity, planetary plus relative vorticity, an evolution equation for that. So here's the planetary vorticity, and here's the vorticity due to the turbulence, and the vector potential for the magnetic field. Now this is a nice test problem because it's only two-dimensional, but as I mentioned earlier, it has non-trivial dynamics. This acts, the turbulence in this case acts as a negative diffusivity, so it tends to drive jets. So if you wanted to describe this using a turbulent transport coefficient, you need to get the turbulent transport coefficient negative. Okay. So as I say here, what does one expect? Well, this is a very well-studied problem hydrodynamically. For people who are very interested in what happens on Jupiter and in the Earth's atmosphere, and it's well known what happens, that hydrodynamically, small-scale turbulence drives jets via what's called potential vorticity homogenization, and it's the nonlinear Rossby waves interacting with each other. They produce a correlation which tends to drive mean flows via Reynolds stresses. We had a look at the effects of MHD on this, and even weak magnetic fields tend to switch off the jets. Okay. So let me just show you. I'm just going to compare two techniques. I'm going to do the direct numerical simulation using this method, okay, and then I'm going to compare that with direct statistical simulation. So I'm going to do something that you should never do. I'm going to try and do a numerical simulation while we speak, okay, so this could be interesting. So first of all, I'm going to do the direct numerical simulation. Okay, so this is just generating the spherical geodesic grid. Oh, no, it's not doing anything, is it? Okay, I'm not going to try and do that because it's not showing up on the screen.
Try moving the window to
Okay, I won't bother doing this because it's not going to work. Those of you who want to see this can ask me later on. Let me just go back and show you what the results are. Okay, so I'm going to have to go through all these. One of the things you would have seen is that the direct statistical simulation is probably about 1,000 times faster than the direct numerical simulation. But let me show you the results, if I can. Okay, so this is the direct numerical simulation. So I'm forcing small-scale turbulence, and what you can see for these parameter values, I get a jet, this is a prograde jet at the equator, and retrograde jets at high latitudes. And this is the zonal relative vorticity. So this is the zonal velocity, and this is the zonal relative vorticity. So this is the inverse cascade, if you like, or the driving, the negative turbulent diffusivity. And so what we did was we did some running average. This is an averaging procedure. So we average over 10 days. You see this is going to 2,000 days. Days being of one revolution being 1 day. And you see we get these jets, or here I get this jet that wanders, and then I start doing a running average, just like one might do when calculating the EMF. And eventually my statistics settle down, the average settles down to some well-defined mean. And these are just two different values of the forcing, which give slightly different dynamics. Okay? So that to do that calculation took 10 days on a parallel machine. And then this was solving the cumulant equations on this laptop in about 5 minutes to show that, again, a jet is driven at mid-latitudes and the retrograde jets, sorry, a jet is driven at the equator and the retrograde jets are at mid-latitudes. One interesting result just on its own is this was the second order cumulant expansion, which, remember, doesn't include either a cascade or an inverse cascade. And so that means that these jets, at least that we see here, are driven directly by the Reynolds stresses. And so there's been some discussion in the literature as to whether jets are driven by an anisotropic inverse cascade or by Reynolds stresses. And what we've shown here is that at least in this model, you can drive jets just by Reynolds stresses. And here's a close comparison of the DNS and the DSS. And you can see here that the DSS reproduces the shape of the jet quite well, certainly in mid-latitudes. It doesn't do so well at high latitudes, but we have an explanation for that. If we had a magnetic field, for a weak magnetic field, the jets persist. But then if the field is strong enough in both DNS and direct statistical simulation, sorry, I don't have much time, then the jets switch off. Okay. And this is the average of the magnetic field in the direct numerical simulation. This is it in the direct statistical simulation. Okay, so I've run out of time, but I hope I've shown you that direct statistical simulations seem to work fairly well, at least for this problem. So further work is to include the third cumulant, which we've done here, and hopefully you can see by including the third cumulant we can get the behaviour near the poles a bit better. These were fully spectral schemes, which are not very memory efficient, so it's interesting to implement pseudospectral calculations and to look at these higher order expansions and try and work out if there's an efficient way of doing these things. I'm just finishing by listing some problems where I think it might be useful to take this approach. I don't think this approach is useful for all problems, and I have no idea whether it's useful for dynamo problems. What I'm particularly interested in doing is something that was alluded to this morning by Andrew and the other day by Paul, convection in a tilted annulus where the zonal flows are driven by convection. We're interested in doing this problem of the joint instability in the tachocline, where the dynamics is actually driven by an instability, a joint instability of the differential rotation of the flow. Problems where you definitely shouldn't use this, because it's a very inefficient way of calculating this, include homogeneous isotropic turbulence. It would be the daftest way you could do of doing these things, or small-scale dynamos. And problems where I haven't really got a clue as to whether this is going to work or not is MRI in a cylinder, or differential rotation mixing in stars, or the dynamo problem. So my conclusion is that this approach may prove complementary to large-scale DNS and to mean field approaches for certain types, but by no means all types of calculation. Thank you.
Okay, questions please. Nathan?
What's the difference between large eddy simulation and this DSS?
Well, if you did a large eddy simulation where you were actually keeping track of how the large scales acted back on the small scales that you're parameterizing, then that would be similar to this. But nobody ever does that. They just do a large eddy simulation where they put everything in. So this is more expensive than doing a large eddy simulation, because you have to keep track of what is happening.
And I've got a very short question. Why are you so sure that you've got negative turbulent diffusivity or viscosity?
It's not really a negative. What it is, it's the Reynolds stresses driving a mean flow. If you wanted to naively describe this by turbulent diffusivity, then you would have to describe it by negative turbulent diffusivity. In the literature, they either call it an upgradient or they call it an anti-friction. Mike McIntyre calls it an anti-friction.
Because you need some high derivatives which produce stabilization of the product.
So they have to stabilize this by putting in some other dissipative process, like they put in bottom friction.
Okay, Axel?
Regarding the Reynolds stresses, would you be able to apply it to flows that exhibit an Acker effect?
Yeah. So that would be an interesting thing to do. Yeah.
And then when you said the dynamos wouldn't work, but then you mentioned small-scale dynamos. How about large-scale dynamos?
Maybe. Okay. I would say, if you believe that mean field electrodynamics works very well in a parameter regime at high Rm, then this should work as well, but be more expensive.
But would your approach also work at low RMs still?
I'd have to think about that. I don't know. Yeah, probably. Yeah. Yeah.
Okay, Alfred?
So, how do you know where to stop in the cumulant expansions?
Yeah, you don't. I mean,
what must be a relation between the most unstable wave number and another cumulant?
No, I think it's a bit more complicated than that. I think, I think you'd be mad to go further than third order. And then it's a matter of whether you can do something a bit better than third order. Because third order, you're really, for a 2D problem, you're solving a 6-dimensional problem.
Okay, Ruba?
Is there a way to deal with real boundaries?
Yeah. I mean, when I decompose my PDEs into ODEs, so let's say I had a spectral method for doing boundaries, like Chebyshev or whatever, then I would get these evolution equations for my Chebyshev coefficients, and then I would just define the cumulants based on the Chebyshev coefficients. If I was doing finite differences, I could do a similar thing. So I would just have evolution equations for those points, the finite difference points that I had evolution equations for, and the others would just satisfy the boundary conditions. So yeah, there's a natural way. I tend to do spectral methods, so I always think in terms of the evolution equations for the spectral coefficients, but you don't have to.
Okay, Noble?
Yes. My concern is similar to Alfio.
Uh-huh.
So I'm interested in Claudia.
Yeah.
I think you cannot close the equation
No.
without, no, yeah. So in this sense, if you truncate in the second order, so you, as you mentioned, you drop to eddy interaction.
Right.
So in such a case, how to say, negative transport is very natural, I think.
No, so if you include, I mean, we did the third order one as well, and you get very similar results. In fact, you get better results. So by neglecting the eddy-eddy going to eddy interactions, you're saving yourself computational time. That's all you're saying. But you can do the other one, and we have, and the results are better. It's just whether you can be bothered going to that order. I mean, there are some problems which are very well described by eddy-eddy going to mean, but not by no means all.
Yeah. I think if you have the truncation in any order, so it will.
You should solve an infinite hierarchy. That's true. That's true.
Okay. Thank you very much, Steve. Now, ask is going to.
We have the conference photograph now, and during the break, I will open the map where you find your way to the dinner place, which is called the Michelangelo. It's easy to find because it takes the standard map of any of both the green line and the red line, both go to this place. It's in Gamla-stan, as you see, this big place is called Gamla-stan. Here's the metro station. The central station is just the previous stop over here. And so now I show you the speed. So as I said, you get off here. And then yesterday we actually walked this, so you go, the train comes in this direction, you get off the station all the way to the left. And then when you get out of everything, I think you find yourself actually in front of this little street here. That's called Schönfeldsgrund. And then you go up to this one, which has the name Stora Nygatan. Then you go further south. Go up on Tyskabrinken. Tyskabrinken would lead you to the German church, which is a big church over here. If you are around time, you might hear the bells, but maybe not. And then the restaurant, of course, is on this street, Westerlånggatan, at this position. And it's on the right-hand side, and it has a red flag, so it's easy to find. I think if you go to the page, you find, to the conference page, you find, it doesn't go left to it here, but